Hello! Today I'm going to talk about microphone pickup patterns and stereo and binaural recording. First, let's talk about microphone pickup patterns, and to see what I mean about that, let's take a look at two different types of microphones. Let's first look at a typical dynamic or even capacitor microphone. In the case of those types of microphones, let's say for the condenser or capacitor type, there is a sealed capsule, one of which has a metal or foil plate or perhaps aluminized mylar or something that can vibrate, and it's insulated from the back here, so we have a connection across there to conducting pieces separated by an insulator, so that makes a capacitor or condenser. And as this vibrates, it changes the capacitance, and that can be manipulated to turn the change in capacitance into a change in voltage or current to create a signal from the microphone. And the dynamic microphone is similar in construction, just works differently. It has a diaphragm with a coil of wire attached to it. And once again, that's usually in a sealed capsule so that the air inside cannot escape. And once again, this vibrates. That causes the coil to vibrate in a magnetic field. So there's a magnet in here. Goes also inside the coil, as I showed in the previous video. And we pick up the wires off of that coil, and as it vibrates in the magnetic field, that creates varying voltage, which if we have a complete circuit, that can be a varying current. And in either case, we have a sealed capsule. So what is the microphone sensitive to? Well, we know it's sensitive to sound waves. So here come the sound waves to hit the microphone. They make the diaphragm vibrate, and off comes the electric signal. But what about sounds coming from the side? Well, in the case of these two types of microphones, sound coming from the side is going to create a pressure difference between the outside and the inside, and the microphone is going to pick up sound from the side just about the same as sounds from the front. And that also goes for sounds from the back. Let's get this second microphone out of the way here. Sound comes from the back, and it's going to go around and diffract to the front. And the higher frequencies may have a bit of a problem here. We may not pick up high frequencies from the back as well as high frequencies from the front, but for the most part, in most of the frequency range, especially if the microphone is very small, we're going to get a pressure gradient on the front, and the microphone is going to pick them up equally. So it picks up sounds equally in all directions, or omnidirectional. Omni being a Greek word for meaning all. So an omnidirectional microphone is going to pick up sounds in all directions. But let's take a look at a ribbon microphone. The ribbon microphone has a magnet. I will show like that, although that might not be the exact shape. And inside is a ribbon of aluminum. Usually it's corrugated. In fact, I think it's always corrugated. And that's suspended between two supports, which we can pull the electricity off of. So here we have a ribbon suspended in a magnetic field, and as that ribbon vibrates, it's going to cause currents inside the ribbon that can be picked off, and there we have an audio signal. But let's look at this from the top. There is our ribbon, there's our magnet poles, and sound coming from the front is going to make the ribbon vibrate. Sound coming from the back is going to make the ribbon vibrate. In this case, it's a velocity-sensitive microphone because it's not sensitive to the pressure, because whatever sound comes from the front also diffracts around to the back. And once again, it's not sensitive to the pressure because the pressure is pretty much the same on the front and back. So it's sensitive to the velocity of the air hitting it. And what happens if sound comes from the back? We get exactly the same thing. The microphone is going to vibrate, sound is going to diffract around, and the pressure is going to be pretty much the same on both sides, so it's, once again, velocity sensitive. Let's redraw that real quickly to get the clutter out of the way. Here are our two magnet poles, there's our ribbon, and here is a sound coming from the side. So now we don't have the air molecules impacting the foil in the same way. Instead of coming from the front or the back, they're coming from the side and pretty much just go right by and have no effect on the foil at all. So that means that a ribbon microphone is going to be sensitive to sounds coming from the front and sensitive to sounds coming from the back, but not very sensitive to sounds coming from the side, and sounds coming from different angles will be appropriately picked up by the microphone. So this is not an omnidirectional microphone, but it is a bidirectional microphone. So there are two different types of microphones that have different pickup patterns based simply on the construction of the microphone. So let's take a look at how these pickup patterns are determined and look at what they are and how we can manipulate microphones to have different pickup patterns. So what we're going to do is take a microphone and take it into an anechoic chamber. This is a room that's lined with foam blocks that are wedge-shaped. Here's a picture of what they look like. And the theory is that we have these wedges of foam, which are going to be sound-absorbing foam, and as sound hits it, it's going to not only be absorbed by the foam, but any sound that does manage to reflect off will kind of reflect down into this valley and eventually be completely absorbed. And so an anechoic chamber is completely surrounded by these, and they also make these that work on radio frequencies for testing antennas. And the floor of an anechoic chamber is going to usually be a wire mesh so that we can have that sound absorbing material below as well as all around us. So that is an anechoic chamber, and of course what that is for is to make sure that sounds are not bouncing around from here and there, and so we're getting a pure test of what's coming to the microphone from some source. So inside the chamber we have something like, well, we'll put a microphone in the middle, just draw it like a little lollipop there, and we'll have something like a loudspeaker some distance from it in a particular direction. And what we're going to do is adjust the sound probably to some average power, or maybe even the peak power the microphone can accept. I've never done such a test. I just have a good idea of how it's done. But we're going to set it at a certain power, and we're going to make that our reference, and so we will call that 0 dB. Remember that decibels are a ratio, and so what I'm simply saying is, let's say that I'm getting a power from the microphone of, let's say, 1 milliwatt. Well, then we're going to say, okay, 1 milliwatt is 0 dB. In fact, there's even a measurement that would be called dBm, but we're not going to use that particular type of measurement. And if you don't understand decibels very well, you should go watch my video on decibels called A Quick Look at Decibels, where I explain what I'm talking about here. But just remember that dB is a ratio of powers, and so I'm simply setting the starting point here and calling it 0 dB. So if this increases to 2 milliwatts, then this will become plus 3 dB. So if we double our power or we cut it in half, that is 3 decibels. So if we double our power, that's going to be positive 3 decibels. If I cut that in half, then I'm going to have minus 3 decibels. And so that's just simply a logarithmic scale in how it comes out. And every time we double, we get 3. Every time we cut in half, we get 3. And another interesting thing about the 3 decibels is that's the point in our hearing where we can tell the difference. So if we double the power, we can hear a difference. At least that's under normal conditions. If you're sick, have a sinus infection or something, you might actually become more sensitive and be able to tell a smaller difference. But generally, we can hear a difference of 3 decibels. So we're going to call whatever power we've set 0 dB, and we are now pointed at the sound source, and so that's going to be 0 degrees also. Now what we're going to do is rotate that microphone. Let's just rotate it 45 degrees. And so at 45 degrees, let's say we still have 0 dB. And we rotate it to 90 degrees. And at 90 degrees, we still have 0 dB. So what's that telling us? That's telling us that as we rotate the microphone, its sensitivity to the sound coming from that source is not changing. And let's say we turn that around and point it directly away, and we still get at 180 degrees. We still have 0 dB. So the signal doesn't get louder, it doesn't get quieter, it stays at the 1 milliwatt that we've set as our 0 dB point. So what's that tell us about the microphone? It's an omnidirectional microphone. It picks up sound the same way in all directions. Now what we're going to do is make a plot of this. So I'm going to make a circular graph over here with concentric circles called a polar plot. And since we know the microphone is going to be most sensitive pointed directly at the sound source at 0 degrees, that's the way we're designing this test, we will make our outermost ring, our biggest ring, 0 dB, meaning that's our maximum power at that point. So anything less is going to be less power, so we're going to get closer to the middle, and we'll also plot that according to the direction of the microphone. So at 0 degrees, we have 0 dB. At 45 degrees, we still have 0 dB. And so we go all the way around the circle, measuring at every appropriate point, and I'm not trying to make those zeros, those are just dots on the scale. And so this particular microphone at the frequency we're testing it at happens to be omnidirectional. Now I mentioned that an omnidirectional microphone might be slightly cardioid at high frequencies. So let's say that's the case here. What's going to happen is when we get to 180 degrees, we're going to get something less than 1 milliwatt. And so let's say we get, well, this, for the sake of easy math, we get a half a milliwatt. So that's going to be minus 3 decibels at this point. And so that would bring us into the next line. It would be appropriate to make each of those lines 3 decibels. So make it more dramatic. Let's make that minus 6 decibels. So that's actually a quarter of a milliwatt. And so that would put us at the next line down at 6 dB. So here's our plot, and so we get a cardioid in that particular case. So that's the way that polar plot is made. And I kind of jumped the gun here and showed a cardioid shape, but of course the next thing we want to do is do the same thing. Probably should have left these things up here. Let's see, put the speaker and the microphone and erase these numbers here. And so we're going to do the same thing with a cardioid microphone and see what we get. Now this microphone has been modified. It has our capsule. I don't know the exact physical way this is done. I've never looked into it, but we'll make this a dynamic microphone. There's our, maybe I should have made it a condenser microphone to be more simple. But we're going to put some ports in here in the right place. This capsule is going to be carefully shaped and carefully ported, so I'll make it long because we can. Put some more ports in it or whatever. Don't know exactly how this is done, but this is an idea. Now it lets some sound into the back in a particular way such that sound coming from the front affects it normally, but sound coming from the back comes into the chamber, and as the diaphragm is trying to push back, sound comes from the back and tends to push it forward. So when sound comes from the back, some of the energy goes in these ports, some of it comes around and pushes on the diaphragm, and the energy coming in the ports counteracts the energy hitting the front of the diaphragm, causing it not to move. So sound coming from the front does not do that, sound coming from the back does, and that causes this to be not sensitive to sound from the back, but sensitive to the front. So what would we call this? A unidirectional microphone? We could, but we have different names for different amounts of this effect. So let's take this microphone and just do our little test here again. And so we set it up, pick off our sound, calibrate that to be 0 dB pointing at the front, and now we're going to turn that microphone 45 degrees and do it again, and now we find we have 0 dB pointing ahead, but let's say we have negative 1 dB. I'm just making these numbers up. And we go to 90 degrees and we have negative 2 dB, and we get on to 180 degrees and we have, let's say, negative 9 dB. So it's a big difference. 9 dB is going to be doubling. So that's going to be 1/4, 1/4, that's going to be 1/8 of the energy being picked up when the microphone is pointed the wrong way. And so what we're going to do is our little plot here. So here's our chart. There's our concentric rings. And I'm going to get rid of that because it's going to be too hard to see. We're just going to put a little dot in the middle. And we're going to get a curve where it's 0 dB, smaller, and it's going to be something less there. It's going to, there'll be different shapes. I'll just make this one look just like that. And so as we get further and further to the back, we have a small drop off, then a sudden drop off to where it has very little sensitivity pointing to the back. And notice the shape of this. Well, let's turn that around. If we put a little different shape to it, oh, look at that. It's sort of, maybe sort of equal to that. It's sort of heart-shaped, and this is called a cardioid. And not only in microphones where there's a mathematical description of it. In fact, if you take two gears and you make this gear stationary and put a pencil here, and you rotate this gear around that gear, as this gear rotates around and rotates itself, it will make a cardioid shape. So that's what that is called. It's called cardioid because it's heart-shaped. And so what do we call this particular microphone? It is a cardioid microphone. Picks up more from the front and then less from the back. There are some variations on this theme. You don't hear them too often, but engineers might use them. So let's take a quick look at the typical cardioid. So there's our microphone. The cardioid has a shape or a pickup pattern, something like that. If it has more sensitivity to the back than this one, it has a shape more like, okay, is that a good drawing? Good enough. Notice that I'm just going to move my little dot to right there. So it's almost a circle, and notice it's less sensitive to the back than to the front, but not quite as drastic as the cardioid. That's called a subcardioid. And now we have others that have a shape that looks pretty much like the cardioid, but they have what's called a lobe. They have a pickup lobe in the back. Let's make this one a smaller lobe. So it starts to lose its energy in these directions, but then it picks it up again in that direction. I'm not sure what use this would be. I don't know where I would use it, but it is something that exists and is called a supercardioid. And if we do the same thing again, there's our cardioid shape getting smaller and smaller here. We have a really big lobe in the back. That's called a hypercardioid. So we have the subcardioid, which is more sensitive to the front than the back, but not as drastic as the cardioid, which is much, just circle that because it's a much more common microphone. So we have the cardioid, the subcardioid, supercardioid, and hypercardioid. But when you go and buy microphones, you're basically going to see two main types. You're going to see the omnidirectional and the cardioid. Those are the most popular types of microphones. But there are some other types. Of course, we talked about the ribbon microphone, which is a bidirectional microphone. So like the cardioid, the bidirectional microphones are good because they pick up sounds from front and back, but not from the sides. So if you want to eliminate those sounds, you have the natural ability of the ribbon microphone to eliminate those sounds, but the cardioid will also eliminate sounds from the back. A very common place to use cardioid microphones, of course, would be people working on a stage at a concert, and you will notice that they have in front of them, here's our stage, here's our performers, and you'll see big speakers called monitor speakers pointed at the performers so they can hear themselves, because with the loudness of the PA system and the way it's pointed at the audience, they have trouble hearing themselves, and so they have speakers pointed back at themselves. Well, what's to keep these microphones from picking up these speakers, and what are they going to get? We talked about that in our previous video about oscillators. They're going to get a sound that goes from the speaker to the microphone, gets amplified back to the speaker and back to the microphone in a periodic sense, that we're going to get that, what we call feedback. It's really an oscillation caused by feedback, but we call it feedback, and we don't want that. So if they have a cardioid microphone, that cardioid microphone is going to pick them up, but not pick up the monitors. So that's one very common place for that. The ribbon microphones are often used in venues where there's people and people on the stage, particularly auditoriums where people are talking but they don't have those monitor speakers. They will often have ribbon microphones because of the fact that they will pick up the speaker but not sounds coming from the sides. But more often you probably find them with cardioid microphones these days because once again you want to pick up the speaker but not sound from around them. And also, like in churches, auditoriums, you're going to have that problem with feedback coming from the speakers, which are pointed at everybody. So if you have a cardioid microphone, it's going to tend not to pick up those sounds and therefore not repeat them and cause feedback or feedback oscillations. But what do we do if we need even more directionality? There's multiple ways to handle this. Probably the cheapest is to use multiple microphones. You may see this occasionally. Sometimes you will see, like, a person will have a lavalier microphone like this, but there will be two of them instead of one. Or they'll be talking at a podium and there will be two microphones pointed at them instead of one. Well, what's with that? Now, it's not like the olden days when you'd see, in fact, even maybe now, where you see somebody talking on the news and there's 30,000 microphones up there because each news service has their own microphone. But this is a different purpose. Those two microphones are used like a directional antenna. I talk about those in antennas down the road in communication circuits, but it works on the same principle. If we have two microphones, let's draw one here and draw one here, and they're just simply fed together, mixed together, either in the mixer or before, most likely in the mixer, equally. And what's going to happen if a sound comes from here, like from a speaker, somebody's talking, it's going to hit both microphones at the same time. So the signal is going to come out in phase down through here and just build on itself. So that's no problem. But what about sound coming from the side? Well, at the right frequencies, the sound coming from this side here is going to hit that microphone first, then that microphone. That's going to cause a slight delay. If you can see what I'm trying to say there, here's our timing. There's the right microphone and then there's the left microphone, slightly delayed. And if the delay is perfect, we get the right microphone and the left microphone and they completely cancel each other out. And other frequencies, they will somewhat cancel each other out. So that's the purpose of sometimes using two microphones. It makes it basically a bidirectional microphone, unless these are cardioids, which means they're not sensitive to the back but sensitive to the front. And that increases, well, it's going to do something like this. Here's our cardioid shape, but here what we get there is probably, I've never tested this, we get a bigger lobe to the front. I'm just going to draw it as a bigger lobe. So there's the microphone. So more sensitive to the front, less sensitive to the back. We might get a bit of a lobe to the back when we do this. I don't know, but that's a possibility. But we're going to get more sensitivity to the front if we use two microphones in this particular fashion. But there's another way to do this, especially if we need a lot of directional discrimination. And this has some history. I remember back in the 60s, there was an article in Popular Electronics or some magazine of, hey, let's make a microphone by taking a whole bunch of tubes. And at these days, PVC was quite readily available and cheap. Just, your basic irrigation pipes. And we'll make a bundle of them of different lengths. And this will go to a funnel and put a microphone at the end. I'll just draw a regular microphone here. And the idea is that sound coming from the front is unaffected by the tubes, but sound coming from the side first goes down this tube, then that one, then that one, then that one, then that one. And so the sounds interfere with each other and tend to cancel each other out. So this will be very, very sensitive in that direction, but not very sensitive to the sides. It might have some sensitivity to the back because it's being pressure sensitive microphones would pick up some sound from the back, but be very, very sensitive to the front. Well, shortly after that, someone discovered that, hey, you don't need to use multiple tubes. Make one tube and put a bunch of holes in it. Just drill a bunch of holes in it. And that will act, once again, with our microphone here, presumably a cardioid mic to reduce its sensitivity from the back. The idea is that the different holes would act like the different lengths of the tubing. And then the next step was, well, we don't need a bunch of holes in there. Just put a slot. I'll just draw one long slot, but for rigidity, there would be some breaks in it, so I'll just draw those later. There we go. Some breaks in the slot. And once again, there's the microphone. And this does the same thing. Sounds from the side tend to interfere with each other and not be picked up well, but sounds from the front are unaffected. And you'll see these fairly often. They well, there's a picture of one right there, and these are called a shotgun microphone. And so they are very sensitive to wherever they're pointed, but not sensitive to the sides. Very common because it's a very inexpensive thing to make. But another thing you might see is a parabolic microphone. These are even more sensitive because they concentrate the sound. So what we do is we have a parabolic reflector. This is rather exaggerated with a microphone at the focus. Usually they're a little less deep than this, but that's a good approximation of a paraboloid. And the idea is that sound coming in, I'm going to draw these straight. I've been drawing them curved just because we're used to seeing them, but if the sound is far enough away, you know, if we're here it's circular, and notice as I get further away from it, the circles get bigger, so eventually they're pretty much straight lines. So we're assuming that these sound waves are coming in as straight lines on the parabolic microphone. And what's going to happen is when these sounds hit the parabola, the distance between here and there, between here, here, and here, is the same as the distance between here, here, and here, and between here, here, and here. And so with those equal distances, it turns out that this wave comes in and reflects off in such a pattern that all of this wave here, so there's our wave front, by the time it goes down the parabola and reflects into the microphone, all of that hits the microphone at the same time. And I'm going to have to redraw this to draw what happens when we're off axis. So if we're on axis, not quite as good an approximation there, but when we're on axis, a sound comes in, all of the energy from this wave comes in, bounces off, and hits that microphone at the same time. But what if we're coming in from the side? Well, two things happen, but the most important is it hits the reflector and everything concentrates, going to be off to the side. Or if it comes from over here, it's going to be over here. So it's going to, the concentration of sound is going to miss the microphone. And less important to audio, but very important to optics, is it doesn't all focus in the same place. And so the sound simply doesn't focus on the microphone, it focuses somewhere else. So the microphone doesn't pick up those sounds as well. Of course, a real parabolic microphone is not going to be so deep because that would be expensive to make. It's going to be much shallower. And so I'm just drawing a shallower paraboloid. It's basically, if we draw that deep paraboloid again, it's going to be just that part of it. Here we just eliminate all those parts there. So we have this, the bottom part of the paraboloid, but it's still paraboloid, and our microphone is going to be mounted somewhere like right around here, and we get the same exact effect. And typically that will be a cardioid microphone, so that it doesn't pick up sounds from the sides very well. So we don't want those sounds picked up, just sounds coming from there and reflecting into the microphone. This works very well, and it concentrates the sound, so it not only is directional, but it is also amplifying. And so you can point this at people or whatever and pick up conversations. You don't want to do that in public unless the people consent. But one place in public where the people do consent is football games, and they want to get the sound of the quarterback calling his signals. And you'll see in football games there will be one or more people around the sidelines carrying, usually just handheld. They have their hands on the edges of the parabolic reflector, pointing them at the quarterback to pick up his sound. I don't know if they ever run a quarterback's microphone into the broadcast. They could. I don't know if they ever do, but you will almost always see somebody with a parabolic microphone at these football games. The problem with them is that they only work well for frequencies with a wavelength smaller than the diameter of the reflector. So when the frequencies are lower and you have a small reflector, that's only going to pick up very high frequencies very well. But of course, it's the high frequencies that make sound intelligible, so it's what you want. But if you want high fidelity, well, I don't know off the top of my head, but it seems like I remember to pick up a sound of 100 hertz, you'd have to have a parabolic reflector that's something like 6 or 7 feet in diameter, maybe even bigger. Something like 9 feet is sticking in my head, but maybe that's for 20 hertz. So not going to work well at low frequencies. And so at high frequencies, they're great. They pick up sounds from this direction. They're reflected in, concentrated on the microphone, but lower frequency sounds, it's basically, they're going to not be reflected, and what you have is a cardioid microphone pointed in the wrong way. So they have their drawbacks, but for frequencies with wavelengths shorter than the diameter of the reflector, they're absolutely great. Now the pickup pattern for these is not perfect. If we draw the pickup pattern, it's going to have a long lobe in the front, but it also tends to pick up some sounds from the back, so it's going to have a lobe to the back, and it also tends to have some side lobes, which means it picks up some sounds from the sides. Once again, that can be mitigated with the cardioid microphone. And by the way, I forgot to show the pattern for a shotgun microphone, and it's very similar. It has a big pickup to the front, a small one to the back, and it has some side lobes. And I don't know about ones that head in other directions. I know that directional antennas tend to have lobes in all kinds of directions, but basically it's mostly sensitive where it's pointed, a little sensitive from directly behind, and a little bit to the sides, but mostly it picks up what we're interested in. And how many dB, I don't know, you'd have to have the scale here. Let's say this is 0 here, and this is minus, let's say 3, minus 6, or whatever. So let's make this a little more drastic. Let's make this maybe 3 dB, 6, 9, and whatever. So whichever direction we're pointed, we're at 0 dB, 3 dB down, 6 dB down, 9 dB down, and so we get a drastic drop in its sensitivity as we point away from the object we're looking at. So those are different types of directional microphones and how they might be used. One thing I forgot to mention is on omnidirectional microphones, the size of the microphone can have an effect on its pickup pattern. So once again, an omnidirectional microphone picks up equally in all directions, but let's draw that microphone here with our pop screen on it. And it's going to be omnidirectional, except sounds from the back are going to have to refract around the body of the microphone. So frequencies with wavelengths smaller than the diameter of the microphone are going to have a little bit of trouble refracting around. So a big diameter omnidirectional microphone will be slightly skewed. Let's just kind of draw a little bit of a little bump in there. It's not, maybe it might even be worse. At higher and higher frequencies, it will be worse. So at high frequencies, you might end up with something that looks more like a cardioid than omnidirectional. So if they really, really need the omnidirectional characteristics of the microphone, they will make that microphone barrel very thin. And I'm drawing about 5 or 6 millimeters, and that would be the ideal with no dust thing on it, just to show the microphone. And this will not affect frequencies in the audio range. So as long as you're below 20 kilohertz, a microphone of this diameter will be truly omnidirectional. But as we increase the size of the microphone body, it becomes less omnidirectional, and the higher the frequency, the less omnidirectional it is. So the body of the microphone can affect the pattern of the pickup. Now, another type of microphone I want to talk about is not really a pickup pattern, but the way all sounds are picked up by a certain design of microphone, and that is a boundary microphone. And the idea here is, well, let's first of all just use a regular microphone. Let's say we're in our concert hall or wherever our other venue is, and here's our microphone. And it's going to pick up sounds from our instruments, and it's also going to pick up reflections off the walls and off the ceilings and off the floor. And all those sounds are going to come in at different phases because of the delay. So the sounds coming in directly, they're going to peak and valley at the same time, but sounds coming from the side, depending on where they're reflecting from. Directly off the side, they might be just a little bit late. Another part of the wall, they might be completely inverted in their phase and cancel out. So we're going to get a great modification of how the sound comes into this microphone. Now, this is the way we hear things normally, but our auditory system is very good at processing sounds to make them such that we can make them intelligible. For example, you know that you can be in a crowded room with lots of people talking, and you can zero in on a conversation if it's close enough for you to hear it all, and you can kind of drown out what else is coming in. But if you go to that same room and put a microphone in the same place and listen in that microphone, you can't do the same thing because our auditory system is tuned to the shape of our ears. I'll talk about that down the road a little bit, but it's tuned to the shape of our ears and the shape of our heads, and has learned how to modify the sounds in our brains so that we can hear differently than what we pick up with a microphone. But it was discovered in the 1940s or 50s, maybe a little earlier, but developed in the 50s and especially in the 60s and 70s, that if we put a microphone or series of microphones close to some kind of a barrier, like just put a microphone up against a wall. So there's our microphone put up against the wall, that there is an effect that happens in this area here. We're talking about very close to the wall. A boundary microphone might be just a few millimeters away from the barrier in the microphone. A phenomenon happens here where the sounds coming in, even if they're out of phase because they're coming in from different directions, reflecting off different surfaces, they have trouble moving through this area in such a way that it tends to put them back in phase. So here comes these two sounds out of phase, and by the time they hit the microphone, they are now in phase. And so this type of microphone can be used to pick up sounds in a room, makes these sounds sound more like we hear them naturally, like they've been processed by our brain. And so probably the most common place you might see these would be in a conference room. So there's a table and there's a microphone that looks something like this. Here is an actual boundary microphone, and that's put on the table. And the sounds are picked up of the people around, but it's not picking up the bouncing off the sides of the room and such that ruins the sound for our ears. If we try to listen on a microphone, it sounds much more natural. But it doesn't, quote, color the sound the same way as a regular microphone picks it up because of that boundary effect with that microphone, or possibly multiple microphones that are in a small holder right above. This is not much bigger than actual size, just a few millimeters above that barrier. So that makes a much better sound pickup in a room where there's echoes coming in. And so these might be used in a conference room. They might be used in a performance studio where they want to pick up people on the stage but don't want to mic the individual people like you often see these days, which certainly works better, but you don't have that microphone in their face. Or if they want to pick up the sound of feet on the floor, like dancers or marchers, they might put these on the floor. And in fact, that's a disadvantage of them. If you have this on the table and somebody starts tapping their fingers on the table, guess what you're going to hear in the microphone? So they can pick up unwanted sounds from the surface that they are attached to. But that's the boundary microphone. Like I say, not really a pickup pattern, but I think it kind of belongs here because it has a way of picking up sound in a unique way that it eliminates the echoes that we usually hear on a regular microphone. So next thing I'm going to talk about real quickly is stereo recording. It's not a difficult topic. Well, in stereo recording engineering, it's going to be a lot more difficult, much more than I need to go into here, but you're going to have multiple microphones. You need to mix them together properly to get the proper stereo effect. But the idea of stereo recording is to use two microphones. I'll space them an arbitrary distance apart. And this time, instead of going together like when I talked about using two microphones for directionality, they go to separate channels, or right and left channels. And you're familiar with that. Of course, you've used headphones. You have to make sure you get the right one on the right and the left one on the left to hear the sounds the right way, because we have one microphone picking up, I'm into classical music, so I think of symphony orchestras, and that's a good standard of where things are going to be. So we have our violins over here, our violas there, cellos, basses, woodwinds, and brass, and the horns are usually in the back. We have some brass here and some percussion over here. And so we pick up the violins over there, the violas in the middle, the cellos and basses there, and the woodwinds, percussion, or horns and percussion in their proper places, except for some people who like to kind of mix them around, but that's the standard arrangement of a symphony orchestra. And you can hear everything where it's supposed to be. And of course, if it's popular music, you hear the elements of the band in different places, and it gives a pleasing sound. And not too much to say about that for two microphone recording, except, well, if you get the microphones further apart, you're going to have better separation. You're going to, like if I have this microphone closer to the violins than to the basses, I am going to definitely hear the violins on the left and the basses to the right. But if I have these microphones close together, there's not going to be much difference. So I need some separation. So you may have stereo microphone on your camera, or even your phone camera. A lot of cameras will have a little left and right microphone about a centimeter apart. That's not going to really make much difference. But it will make a difference if we have two microphones that are cardioid and we have them close together but pointed in different directions. So I'll just draw lollipops here. So one cardioid mic is pointed that way, one cardioid mic is pointed that way. That's going to really help the stereo separation. But it's even better to get them further apart. Of course, then we have phasing issues. So there's all sorts of issues that can happen when we get to recording. For the average person, it's probably best just to put the microphones fairly close, but use cardioid mics and point them apart. Then we won't have the phasing issues that you would have if they're further apart. But that's for stereo engineering, not for just talking about the basics. So that's what stereo is, having multiple microphones. Back in the mid to late 70s, there was a big thing about 4-channel recording, and the idea was to be able to have 4 channels and pick up sounds all around instead of just in front of you. And so you would have speakers in the front and speakers in the back, sounds like surround sound. Well, we still have that in surround sound. A big thing in movies is to have that kind of recording where you might have 4 or 6 or 8 or even more channels. And of course we have 5.1 Dolby, which means we have 5 channels plus a subwoofer, that's the 0.1. And so we have 1, 2 in the front, 2 in the back, and then 1 in the middle to pick up the voices and stuff. So when you're watching a movie, people talking are pulled to the middle and other sounds are placed around you. It can be very spectacular. That's what's called discrete surround sound, where you have multiple channels, where you have discrete microphones and discrete channels, but there's also ways to mix that together. So we can take those rear channels. So there's our microphones pointing to the back, and these go into our mixer normally, but the 2 back channels, one has its phase flipped. So the 2 front channels are going in phase, the 2 back channels are going in out of phase. And this, of course, is done in the mixer, and what that does is sounds coming from the back actually get canceled out. But what we can do is mix those in to these 2 channels. So those 2 channels in the back are canceled out and you can't really hear them in the front. But then at the listening end, we take that one we flipped and flip it again in the speakers. It can be done electronically or just by rewiring the speaker. And that picks out those sounds again. And you can once again hear those sounds in the back. So we take 4 channels, mix them into 2 by flipping the phase of 1, mix them into 2 channels, and then flip that phase, have basically our wires going to our front speakers. And then to the back speakers, we have left, right, left. Let me do this in colors just to help make sense of this. So to the front speakers, we have our 2 black wires. To the rear speakers, we have our 2 black wires. And then we have our 2 red wires going to the front speakers. And I'm going to draw these like that. So we have our black, red going to our speakers normally, but in the back, we do that flip. So if I label this out, black, red, that's the coding on the speakers. On the rear speakers, we go normal, black, red, then red, black. So we flip the wires on just one speaker, and that decodes what I just did. So basically, we're flipping the wires on one microphone, mixing it into 2 channels. Then when we come back out, we flip the wires on one speaker. And notice this is the rear, this is the front. So the front speakers get the sound normally. The rear speakers, we either electronically or physically flip the wires, and that directs those sounds to the back. Theoretically, it doesn't work because there's only a 3 dB difference between the front and the back when we use this method. But the audio system in our brains is awfully good, and it can separate that out much better than is theoretically possible. And trust me, it sounds great if you do this. For a long time, I don't know if this is still done, but for quite some time, movies that were sold commercially on VHS, for example, which had 2 stereo channels, almost always mixed in sounds using this method. So if you didn't know it, you wouldn't hear the difference. But if you just simply put a second set of speakers at the rear of your room and flip the wires on one of those speakers, you would get that surround sound that was almost always put into movies that were sold to the home market back in the 80s and 90s. I don't know if they still do this with DVDs, and I don't know if you stream movies, if this is still done. But even if it isn't, it actually creates a pleasant ambiance that might sound good to you. So just a little hint there. If you do not have discrete sound such as 5.1 Dolby, if it's just straight stereo sound, flip the wires on one of your rear speakers and see what you get. It won't hurt anything, and it might sound good to you. Otherwise, it may just sound a little echoey back there, but that's the way things would be back there, so it might be a pleasant sound. So that is a little off of what the main topic of this video is, but that's something that they did. And while I'm talking about that, there was another way of doing that, where they took the 4 channels, and the idea here was to manage to squeeze all 4 channels on a vinyl record. Can you do that? Well, yes, of course you could use that method I just talked about, which was, it had various names. It was called quadraphonic sound. It was called SQ or QS, depending on who you were talking to, or matrix surround sound. That's the generic name. But RCA said, let's make 4 actual discrete channels in the one groove. So what they did is they took the 2 front channels and the 2 back channels. So there's our 4 channels coming out. What they did was a little weird. I'll try to explain it. But what they did is they put on the record a radio frequency tone. Basically, it's supersonic, but it acted like a radio frequency. I don't remember the exact frequencies, but basically it was high enough frequency that we would not interfere with the regular audio frequencies. And we would treat that like an FM radio broadcast. They would treat it exactly the same. I'm not going to go into the details about that here. I do talk about FM broadcasting in the communications class, but they treated that ultrasonic signal on the record as a FM radio transmission, and they would transmit the information from the rear microphones. Now what they really did is they mixed all of them together, and then what they would transmit on the back was a signal that could be used to separate those 4 channels. And so if you listen to the record on a normal record player, you'd hear 2 channels, but it's actually all 4 channels mixed together. But if you had a receiver and a proper needle, that took a special needle, a special cartridge, and special electronics. I used to have all of it except for the special needle because they became impossible to find. But I had that at one time, and it even had the record. Here's a picture. If you look on Wikipedia for a picture of a 4-channel record, that's my record. I put that picture on Wikipedia. And you can see the little rainbow effect from that high frequency carrier that's in the groove. But anyway, if you listen to it regular, you hear all 4 channels in the front. But if you have all the equipment, the proper needle, the proper amplifier, and the 4 speakers, you could hear 4 separate channels. Unfortunately, that one record, they basically took the orchestra and all the echoes in the concert hall and mixed them into the front, and it sounds absolutely horrid. And so that was the wrong idea, but that's what they did. But in other venues, that might sound pretty good of having those 4 separate channels. And that went absolutely nowhere. So we now still have multiple channel sound. It's called Dolby 5.1, or I think it was even Dolby 7.1 now. So you have 6 channels around you and 1 in the middle, plus the subwoofer. So it's still a thing, but the experiments they did in the 70s kind of died out. So that's was surround sound. A little bit of a tangent from what we're talking about, but it's vaguely related, so there we are. Okay, so that was stereo and surround sound. Got a little more complicated than I planned, but you got the idea and hopefully picked up something interesting, even though the stuff about surround sound in those days was obsolete. But today, once again, we have 5.1 and 7.1 surround sound still, so it's still a thing. So the last thing I want to talk about is what's called binaural recording. And this might be confused with regular stereo because back in the 50s or so, some companies were referring to stereo recording as binaural recording. What do I mean by binaural? Bi meaning 2, aural meaning sound, 2 sounds. Sounds like stereo to me. But in today's context, binaural means they've done some special things to process the sound to try to make it work as if we were actually hearing it with our ears. The original experiments were to take a styrofoam dummy head or a plastic head or whatever, put some fake ears on it or whatever, and stick microphones where the eardrums would be, and use that to record, because that would give us our sounds exactly like we pick them up, because our head does interfere with our sounds. Now, there's a bit of a fallacy there, because everybody has unique ears. Even our right and left ears are different. And as we grow in our first few months of life, our brain tunes to our particular ears. And if you have an injury and have to have your ear replaced or modified, or it changes the shape of one of your ears, for a short time, you'll have trouble telling where sounds come from, because your brain has to recalibrate to your new ear. And so I find it a little dubious. I think, oh yeah, we'll make fake ears and it'll sound just like you. No, it's not going to sound just like you. A lot of times they don't bother with the fake ears, but they do have the dummy head that with the microphones in it to try to record the sound. Now they use modern digital processing to simulate that, to create what are called binaural recordings. And if you want to hear what they sound like, there are some binaural recordings on YouTube. There's some demonstration recordings on the binaural article in Wikipedia. I have listened to them, and I can't tell the difference, really. At first I said, oh yeah, well, yeah, the binaural, it sounds like the sounds are just outside my head. Normally stereo sounds pretty much inside your head. These sounded a little bit outside my head. But then I listened to some other binaural recordings and it was all inside my head. Then I listened to some standard recordings and some sounded inside, some sounded slightly outside. So I really can't tell the difference. I thought that when it sounded slightly outside my head instead of all inside, it was a slightly more pleasant sound. And after listening to a recording for a while, it tends to expand and sound a little more outside than inside. So my brain kind of gets used to it and tries to pull it out. So listening in headphones is its own experience, because everything's inside your head. So my personal experience with binaural recording is I really can't tell the difference between a binaural recording and a well-engineered regular stereo recording, but your mileage may vary. And there's one last thing I want to talk about, which was a thing back in the 70s again, where they have a stereo expansion. I think this is still a thing, because I believe that some sound cards and processing software on computers still do this. And that was the idea of taking a stereo recording. So here's our playback. Here's our little boom box with our two speakers. And if you monkey with the phasing, with the timing of the two signals in the right way, you can actually expand the sound. So normally a stereo recording, you're going to hear sounds either here or somewhere in between. But with this phasing modification of the sound, you can actually expand it beyond, which I thought was pretty cool. Radio Shack sold a number of boom boxes with that built in. I'm sure other people did. And like I said, I think that this feature is still available on some sound cards. And so you can have your speakers, and if you have a expansion function that can expand the sound beyond the speakers, it's pretty much the same thing. And that sounds pretty cool, but it's not the real sound. It does tend to move things where they don't belong. So if you have your symphony orchestra that I like to listen to, and you want the basses to the right and the violins to the left and the horns in the middle, and you find the horns are kind of to the left and the basses are sort of where the violas should be, that's going to be, yeah, that doesn't work for me. But listening to popular music where that doesn't matter so much, it can sound pretty cool. So that is microphone pickup patterns, stereo recording and multi-channel recording, and related topics. And I hope you found this useful and informative. And if you did, please give me a thumbs up. It really helps the channel and helps other people find these videos. And if you want to learn electronics technology and perhaps become a certified electronics technician, or get a jump start in your studies in electrical engineering, you can go to my free course in electronics technology at Vocademy.net. Just sign up and it's all free. As always, a big thank you to my patrons at Patreon and my one-time donors. I couldn't do this without your support. So every time you throw a dollar in the kitty, that makes it so I can keep making these videos. And so I really appreciate it. I wish I could give you all an individual thanks. But being the chief cook, bottle washer, editor, filmer, I don't have a lot of time to individually interact with you. I try to when I can, but I can't make any guarantees. But I really appreciate it, because I couldn't do this without your support. So a big thank you to my patrons at Patreon. I couldn't do this without you. A big thank you to my one-time donors. Those are a big bonus that really, really help. So go to patreon.com/Vocademy to pledge your support, or go to paypal.me/VOCED, VocEd, Vocational Education, and give a one-time donation. A big thanks again, and thanks to everyone for watching.